everyone to the penultimate department seminar series of the semester. It's my great pleasure to introduce our speaker today, Dr. Kyle Bishop. Dr. Bishop is a professor of chemical engineering at Columbia University. Prior to joining the faculty at Columbia, Dr. Bishop was an assistant professor at Penn State, where he was awarded an NSF Career Award and the 3 and 9 tenured faculty. Prior to that, Dr. Bishop performed his graduate studies with Bartosz Jurowski at Northwestern, and he did his postdoctoral work with George Whiteside at Harvard. Dr. Bishop has done some really incredible work in the area of colloids, in particular with assembly and non-equilibrium transport. And today he's going to be talking about some of his more recent work with colloidal robots. So with that, we'll hand the floor over.
Great. Thank you, Wyatt. All right. I'm so happy to be here in person. This is my first in-person seminar in quite a while, so I'm really excited to share it with you. Thanks for the chance to come and share some of our work with you. So I'm going to talk about colloidal robots and what it is that we as a field and community are trying to do, and then a taste of some of the work that's going on in our group in particular. First, a pitch for Columbia and City of New York. So this is an aerial shot of Columbia, and you can see this is the main campus here. This is Low Library. This is Manhattan. You're looking south. This is the Hudson River. And you all are in Boulder, so I assume you like the outdoors. So you will love Central Park right here, and you will love Riverside Park right here, and Morningside Park right here. So Columbia is kind of nestled just above the Upper West Side of Manhattan, and it's a really nice place to be. Okay, another pitch on our department. So we're a chemical engineering department, and we have grown a lot in the past decade. These are the faculty that were in the department in 2010, and now we've grown to 20 faculty members, hiring basically at all different levels and growing in lots of areas. We have particular strengths in electrochemical energy storage, in soft materials, and also in biotechnology. So check us out. If you're sending undergrads looking to graduate school, send them our way. Oh. Okay, so we're talking about colloidal robots. I want you to first think about robots that you may be more familiar with, right? This is a Roomba vacuum cleaner, right? You all know what it is. It moves around by itself, and it cleans the floor of your house or your apartment. And if you think about how does it do that, right? It has sensors and actuators. Those are the building blocks of all robotic systems. The sensors of the Roomba scanner doesn't work that great, but you see there's a bumper, there's a camera, there's various infrared sensors to keep it from running off the stairs, and then there's actuators. There's the thing that the Roomba can do, right? It can turn its wheels to move forward, right? It can turn right or left. It has brushes, suction. And inside it has these really sophisticated control systems that link this sensory information and use it and pass sensory inputs to determine what action it should take. And that control system is designed to perform a function, right? So here the function is clean the apartment, don't break anything, don't destroy the Roomba. So we'd like to do these same types of things in systems that are hundreds of thousands of times smaller. So rather than a Roomba, which is like a fraction of a meter in size, we want to make a colloidal scale robot, which is 3 to 30 microns, so about the size of a living cell. And a colloidal robot should ideally have these characteristics, that it can be dispersed within a fluid environment or a soft environment through which it can navigate. It should be propelled to move, so you're not relying on passive transport mechanisms like diffusion. It should be able to move around its environment in an autonomous way, right, without someone driving it by means of a joystick, for instance. And all of these things should be carried out in a programmable way in order to perform a certain desired function for the given application at hand. Okay, so if we didn't know better, we might think that were impossible to do, but we know that it's possible to make a colloidal robot because they exist, right? They're called living cells. And they provide a kind of existence proof for the types of systems that we would like ultimately to engineer. And this is a video that many of you may have seen, but I like to look at it through the lens of this Roomba analogy that we just looked at, right? So this cell here, that's the Roomba vacuum cleaner. It's moving around a really messy apartment that's full of these red blood cell bean bags. and it's trying to pick up some dirt here, this bacterium that shouldn't be there in the blood. And this is actually a harder task because the dirt is running away from the vacuum cleaner, right? So it has to keep smelling it, feeling around, using mechanical and chemical sensors, guiding its motion, pushing through the obstacles in its environment, and ultimately encapsulating the dirt here, the bacteria, preventing the spread of the infection, right? So these types of things are possible, but we don't know yet how to do them well in synthetic systems. Okay, so these colloidal robots that we're talking about, they aim to perform functions that we find in living systems, but they're probably going to do them in different ways, right? We're not trying to copy biology exactly, and perhaps there's good reason for that, but we're going to solve it in a slightly different way. So here are some of the functions that we would like to be able to do, right? Navigate through these microstructured environments. Maybe we want to be able to store and record information about that environment and transmit it back to the outside if we're looking to do some kind of detection work. Maybe we want to deliver material in or remove material from a targeted site or repair damage in a material environment. So these are the things that we'd love to be able to do. And I'll just point out, that if we were working in a biological environment, you could argue, and you would not be wrong, that we should just use living cells to do this, right? Much of biotechnology is based on that idea. Let's just reprogram biology to do things that we want it to do. But there is still a reason, I would argue, to try to innovate these synthetic systems, is that perhaps they could perform these functions in environments in which living systems are not really happy, right? That they can't survive. So one example of this that just as a motivating example is that of a lithium metal battery, which many of my colleagues at Columbia who work on batteries tell me this is a really exciting battery because it can store a lot of energy for its density. But it has a problem that is the reason why they're not in widespread use, which is that you can form these lithium dendrites that span between the cathode and anode and cause a short circuit. And so one strategy, a strategy that's often pursued in these systems, is let's make better materials here that are super tough and resist the formation of dendrites growing through the separator material, but let's not inhibit the ion transport that's necessary for the battery to function. Another approach, right, one that recognizes the fact that these dendrites are very rare, right? They happen very infrequently and at certain select locations. What if we had a mobile agent, right? I'm drawing it like a fire truck because there's a close analogy here to how we put out fires, right? We don't make everything fire retardant, right? We have ways to respond to a situation when it arises. The fire truck can go and put out the fire, okay? So that's a motivating example where we would love to have these synthetic robots that are not necessarily based on living cells, but based on synthetic systems that can be tailored to different environments. Okay, so there are many ways to propel particles. And let me just kind of step back and give one word about how we approach a problem, right? So I mentioned that we don't know how to make colloidal robots, right? So then you say, well, how do you even know what to do when you show up at lab, right? And the idea is, of course, you break up that problem into smaller sub-problems, and you start to build the pieces that you're going to need to make this colloidal robot. And so one piece that many have recognized is that we need to be able to propel ourselves through different liquid or soft, squishy environments, right? And so that was an area that received a lot of attention, and there are now many ways to propel colloidal particles through different environments. So here are just a few. Often we use external fields, so these are some that we've investigated in our groups, and there are, of course, many others that the field has investigated. So using electric fields, this is a mechanism called contact charge electrophoresis. Using induced charge electrophoresis, here is a photograph from Jin Lee, who's in the audience here. You can wave, Jin. That's his paper that we were able to collaborate on. You can use acoustic energy to supply energy to the system and set up streaming flows that propel particle motion. You can use chemical energy, right, in the form of fuels and catalytic materials to set up concentration gradients around these colloidal particles that drive flows and propel their motion. You can use, again, external electric fields to drive motion by yet a different way, and we're going to talk a little bit more about this Quincke mechanism here today. All right, so the point is we know how to make things move, but these particles are not smart, right? They're arguably the opposite of smart. They're just little rocks, like little pieces of material, and as a result, they don't have the capability of doing different things in different environments or making decisions or in any way changing their behavior as their environment might change. So this no brains means no internal dynamics, no internal degrees of freedom that they could use to guide more autonomous behaviors. Okay, so today I want to talk about two examples where we start to think about different strategies for incorporating internal dynamics into these colloidal robots. And I'll talk about two examples also to highlight two different kind of ways in which our group pursues these problems. And one is the kind of scientific motivation to understand something that we don't understand, and then to leverage that understanding to design something with a functional engineering purpose. So first part of this talk is going to be about understanding, and in particular it's going to be about understanding what you see here in this little movie of this oscillating particle. So we want to know, why is that particle oscillating, and explain what variables in the experimental setup influence the speed and frequency, amplitude of those oscillatory motions. And ultimately, the reason why these oscillators are interesting to us is because particle oscillators have these internal degrees of freedom, like their phase, like their orientation, and as a result, they have much richer collective dynamics, and we'll see some examples of that here in a moment. Okay, and then the second part of the talk, I'm going to talk about a design objective, which is to make particles autonomous in the sense that they're going to respond to gradients in the topography of a surface. So we're going to have a surface here, and it will have regions that are sloping, and we want to make particles that move up the hill towards the top. And the trick is that they're all going to be moving in a common magnetic field, right? So common magnetic field, particles doing different things because of differences in their environments. So we call this magnetic topotaxis, and the key theme is going to be using time-varying magnetic fields as an encoding medium to program these types of autonomous functions. Okay, so this is part one. Let me first just credit the people that did this work. So Jinyan up there, the clown with the hammer, he was the lead author on this paper and really drove this. He was working closely with a senior graduate student, Young Do, who has graduated and since gone off to work. And this was done in collaboration with the group of Monica Olvera de la Cruz at Northwestern University and her PhD student, Hong Yuan. Okay, so this is based on this idea of Quincke rotation. If many of you haven't heard about it, that's okay. It's an old idea. I'm going to walk you through it. So this is Quincke. He discovered this some time ago, over 100 years ago. And what he found was that if you take a solid particle and you put it in a liquid under appropriate conditions to be determined, and you apply an electric field between two electrodes, that particle will rotate spontaneously in a DC electric field. So the key characteristics here is that particle is going to rotate, and it's only going to do so when you exceed a threshold value of the field. So only when the field is large enough will this rotation kick in. Okay, so much later we have a quantitative explanation for what exactly is going on in this Quincke system. And it's based on this so-called Taylor-Melcher leaky dielectric model. And the idea of this model is that we have two homogeneous media, a fluid and a solid particle, and they have permittivities and they have conductivities, which are different from one another, but uniform through space in both the fluid and the particle phase. And there's no charge in either of these bulk phases. If there's any charge, it's all going to accumulate in a really thin layer at the surface of the particle. And then we're going to assume that all the conductivities and permittivities are uniform in space. And this is important because we're going to later have to relax that assumption to explain these oscillations. Okay, so this is what happens when you put a sphere in a fluid, right? You put a sphere in a fluid, you apply an electric field. Very quickly, all the molecules within that sphere become polarized, right? The charge separates within the molecules, and you get a dipole. So here I'm drawing a situation where the permittivity of the particle is greater than that of the surroundings. And so you get field lines that look like this. This is a conductor, remember here, so there's going to be electric currents, ionic currents rather, moving along these field lines. And as a result, they accumulate on the surface of the particle. And when they accumulate, they redirect the field and the electric current around the particle until we get to a stable scenario like this. This happens on a time scale. I'm just going to call it tau NW for Maxwell-Wagner. It depends on these properties of the two materials in ways that are not important here. And then the key idea of Quincke rotation is that if the field is big enough, the time required for this particle to rotate in the field, I should say, first of all, that this particle has a dipole moment which is pointed downward against the direction of the field. That's unstable, right? So if that dipole rotates to align with the field, it will do so. But that rotation takes a certain amount of time, which has to do with how strong is the field, how viscous is the fluid. If these two time scales, one for rotation, one for charging, if they're matched with one another, which they are for certain fields of certain magnitudes, then you'll get this kind of steady state, sustained rolling scenario where it's constantly rolling, constantly accumulating charge. It's exactly like a water wheel, right? If you pour water on a water wheel, right, it collects on top, it's heavy, it causes the water wheel to spin. So the same exact idea is going on here. Okay, so why do we care about this 100-year-old phenomenon? Well, there was a paper back in 2013 by the group of Vinnie Bartolo in which they took this mechanism of Quincke rotation and they used it to drive the rolling motions of spheres on a solid substrate to create Quincke rollers. And these Quincke rollers, turns out, are a really great model system to study large collections of self-propelled particles, so-called active matter. So here's a video from their paper. It's like a herd of buffalo particles rolling along. And they were able to study, the formation of this front and how various perturbations propagate through these systems of dense, self-propelled particles, right? So this stimulated a lot of interest in this Quincke system in order to make these types of model systems to study the collections of these active particles. Okay, and we had interest to use this Quincke system for a different purpose. But when you're starting something new, what do? First you just try to reproduce what other people have done, right? So you say, you tell your graduate student, go do what they did. That was cool, right? And then we'll build the new things that we want to add on to that. And so when Jinian did this, he used the exact same setup that they used in the Bartolo paper, which is two conductive electrodes that are transparent, so we can see the particles through the lower electrode at an optical microscope. It's a mixture of AOT, which is a surfactant, and hexadecane, which makes these micelles. And these micelles, some of them are charged, that's the electrolyte. And you apply an electric field that drives an electric current between these two electrodes. And we just have polystyrene spheres. There's nothing to it, just the simple plastic spheres you buy. And when you apply this field and you see what happens, if you apply a weak electric field, nothing happens. The particles just sit there. If you increase the strength of the field, they start to roll, right? That's what we expected from the Bartolo paper. But then, interestingly, he found that if he kept increasing the field, right, he found that oscillatory regime that I showed you in the previous movie. And this was something that wasn't reported. Well, so I said we discovered it. An anonymous reviewer, who won't be named, pointed out that an obscure reference inside the thesis of one of Bartolo's students made this observation. So we're not going to claim discovery, but we're going to claim to have explained this phenomenon and hopefully also to build on it. Okay, so in quantifying this effect, what we can do is we can look at the speed of all of those individual particles and average them in time and look at what is the time average speed as a function of the field strength. And the colors denote the different types of motion which are identified by a different classification scheme. So purple are the oscillatory motion, pink is the rolling motion, yellow is the stationary motion. And so you can see how there's nothing happening. Then around there's a region where there's this transition to start rolling. They're rolling, and then another region where it's a bit ambiguous, and then they enter this steady oscillatory regime where we can see that the average speed decreases, but the variance in the speed with respect to time increases as the particles move back and forth. So that's kind of the signature for oscillation. So there's a second critical field strength, and we want to figure out what's going on, what sets that second critical field strength. Is it related to the first one? Why are they oscillating? That's the question we want to answer. Okay, well, so inspired by your own little Medlin, I want to give you a quiz. This was something that he did in his Zoom presentations. And you can see here, these are the Zoom icons that I've used in the past to poll the audience on which of these questions would you like to pursue first. So here we're just going to do this by a show of hands. Let me read the options, and then I'll ask you just to raise your hand which of these options you want to pursue. So your goal here, remember, is to figure out why these particles are oscillating. And maybe you look at those oscillations and you say, they're probably due to inertial effects. That's something I would want to consider before making any kind of big deal about this. That's not exciting. Maybe you say, how do the oscillations depend on the AOT concentration? Right? So there's experimental design variables. Let's look at their effects on the results. Or you just want to know, what do we know in the literature about this AOT hexadecane electrolyte? You mentioned some micelles, they're charged. Tell me more about that. Okay, so those are your three choices. So who wants to know about inertial effects? Raise your hand. Thank you. I see a couple. You gotta raise it high. Who wants to see more experiments on the effects of AOT concentration? Oh, okay. Who wants to learn more about AOT hexadecane electrolytes? I think it's close, but I think the winners are the option number 2, do more experiments, right? That's what we told the graduate student. Do more experiments. All right, so I have to go to slide 21. Okay. So here is a series of experiments, just like the ones you saw, but now for 3 different concentrations of this AOT surfactant. So this is 0.5, 0.0, this is 50 millimolar, 100 millimolar, 150 millimolar. So what you can see here is that the field required to induce oscillations is larger, right? You've got to go to higher fields to induce oscillations. Likewise, it seems like a kind of similar trend. You've got to go to higher fields to induce the rolling motion, right? And it's known in the literature that adding more of the surfactant creates more charge carriers, increases the conductivity of the fluid. So this idea that you need higher fields because the charging time is faster, so you need higher fields to get these transitions to rolling into oscillations, that all seems to kind of make qualitative sense. You can also look at the individual trajectories and characterize their frequencies and their amplitudes of their oscillatory motion. And you find that the frequency of oscillation scales in the same way as the rolling velocity does in that Taylor-Melcher leaky dielectric model. So it suggests that this oscillatory effect is similar to the rolling effect that is previously known. Another interesting thing to note is the amplitude of the oscillations. The dashed line shows a case of pi times the radius, which is sketched out here. This is exactly what you would expect if a particle were rolling, making frictional contact with the surface, and just turning upside down. So if a particle, you roll it, turns upside down, you roll it back, turns upside down, it should go back and forth by about that amount. So that suggests that maybe it's just doing this kind of flipping, making frictional contact with the surface. Another poll, last one. Do you want to hear about inertial effects or more about the AOT electrolyte? Number 1, inertial effects. Okay. Number 2, AOT hexadecane electrolyte. All right, that's easier for me to segue to based on what we just talked about. Okay, so there's been a lot of work studying these kind of electrokinetic effects in nonpolar media, and they tend to be mediated by surfactants that create these kind of micellar structures like this one here. This is the reverse micelles of this AOT surfactant. So essentially these are big ions, or big micelles that can be charged, and therefore serve as charge carriers in this solution. So the size we're talking about have a hydrodynamic radius of about 1.7 nanometers. And so the idea here is you have lots and lots of these micelles in proportion to the concentration of AOT, but only some fraction of those micelles acquire a charge. And the take-home message from this slide is that they charge as expected by Boltzmann statistics. So just at equilibrium, some micelles will be charged, very few of them, others will be not. Very improbable that any micelle has, or that many micelles have multiple charges, so they're either +1, -1. And there's a whole theory that's been worked out by Dennis Quincke and co-workers called the charge fluctuation theory, which basically makes this explicit, just looking at how much energy does it take to charge a single micelle, and then working out the statistics to say, you know, if they're Boltzmann distributed, this is how many charged micelles you get. This should then be the conductivity of the fluid. And if you do conductivity measurements as a function of field strength, forget about the fact that the conductivity is field dependent. That's another effect, which is interesting, not explained by this theory. But just focusing on the zero field limit, you find that the zero field conductivity increases with AOT concentration in a way predicted by this theory when you account for the fact that we're operating at such high micelle concentrations that you're also changing the dielectric constant of the fluid as well as the number of micelles. That's why this is faster than linear. Okay, so now we have this picture that there are micelles. They can be neutral, they can be charged, but this is important because it means that charge carriers can be created at any location in solution, and charged micelles can discharge, right, recombine to form two neutral micelles. That's going to be important. Okay, so by process of elimination, we're back to inertia. And here the story is simple, right? Inertia is not important. These particles are small. The Reynolds number is small. The Stokes number is small. So neither the inertia of the particle nor the fluid is relevant to this problem. But I will point out that that was a really good suggestion because it's known that if you have a larger sphere where inertial effects are important, then these Quincke systems can lead to oscillatory and even chaotic dynamics. And in fact, there's a direct mathematical equivalence between the model of this Quincke roller and a model of this water wheel here, the so-called Malthus water wheel, or the chaotic water wheel, that's being fed water from above, and water is leaking out of these buckets at a constant rate. And this simulation is highlighting a regime where that dynamics is chaotic, and it's facilitated by the inertia of the wheel, right? The fact that once the wheel is turning, it wants to keep turning. If you turn off inertia, right, you make this an overdamped water wheel, it will only ever roll, right? That's what the leaky dielectric model predicts. Never oscillations, only rolling. Another side note, these dynamics are actually the same as that of the Lorentz system, where chaos was first identified numerically. So interesting connections. All right. So now we go to slide 25. Okay, so you've done the experiments. You now are equipped to come up with a solution that can help to explain why are these particles oscillating. And I'll tell you, it's based on this process by which neutral micelles become ionized, and the competition between ionization and the migration of ions creates a boundary layer near the electrodes. And this boundary layer turns out to be just about the size of a particle, and it impacts their dynamics. So here's what's going on in that boundary layer. Actually, let's start with the bulk. So in the bulk fluid, you have positive micelles, you have negative micelles. They're moving in opposite directions under the influence of the field, right, in order to sustain the current that's being supplied to the system. And in the bulk, the rates of ionization and recombination are balanced with one another, right? That's what sets the number of charged micelles. Within this boundary region, however, we're going to neglect that the electrode produces any positive charges. It doesn't inject charge into the system. So that means that these positive charges have to be created somewhere, and it turns out you need a region of a certain thickness to create enough ions needed to sustain this current. And so if you balance the rate of recombination, which is related to the rate of ionization in the bulk, with the migration stuff leaving, so this is just an ion balance, right, you learn in your chemical engineering courses, you can come up with an estimate for that length scale of how thick should this region be. And we find that if you plug in the numbers, it's like 10 microns, which is like the size of those particles that we see oscillating back and forth. So this is interesting because this is a boundary layer that's very different from the the usual electric double layer that you find in electrolytes, and it's created by the special electrolyte that's able to ionize and recombine and driven by these very strong electric fields in order to make it a length scale that is competing with the size of these particles in the system. Say what these things are. This is the charge, E, fundamental charge. U is the ion mobility, so related to the Stokes-Dragoman ion. E is the applied field, Kr is the rate of recombination, and NEQ is that equilibrium concentration of charged ions in solution. So all of these things we have to estimate from those conductivity measurements, and then we can come up with this estimate in microns. Okay, so a cool thing happens where you take that new length scale that you've identified and you use it to collapse data that we collected on many particle sizes, many AOT concentrations. Now things start to begin to make sense. If you plot the ratio between the particle size versus that electric boundary layer thickness against the ratio of the applied field versus the critical field that's required in the theory to drive rolling motion, then you can see there's some kind of nice regions of a yellow region where there's no motion at all, a pink region where there's rolling, and this special purple region where there's oscillations. And the key thing to note is that the oscillations only happen in strong fields when the size of the particle is comparable to the size of that boundary layer. A couple observations that are also interesting. If you have big spheres, they extend far beyond this boundary region. They just roll. They don't oscillate ever. If you have small spheres, they don't do anything, right? This is surprising. You put a small sphere in there, you apply an electric field, and it just stops moving completely. It doesn't even diffuse anymore. So how can we explain they're oscillating, they're rolling, and they're not moving? Take the picture of that electrolyte that we developed that has ionization and recombination, and we plug it into the usual Nernst-Planck-Poisson equations governing the dynamics of ion concentrations within an electrolyte. So we have, this is just a conservation equation of positive and negative ions. So ions are transported by diffusion, by electromigration, and then they're created and destroyed by these processes of ionization and recombination. And then anytime you have a net charge density, there's more positive ions and more negative ions, you have a charge density, and that influences the local electric field, which then comes back and influences their motion. So in a steady state system, we can solve these equations, and this is what it looks like around a single sphere, not moving. So if you have a big sphere, this is a big sphere relative to the boundary layer thickness, you get, I don't know if you can see this, but you get positive charge on the bottom, negative charge on the top, exactly what you would expect from the leaky dielectric picture. It's a dipole, it's going to roll, it's unstable, and that makes sense. If you have a small sphere, you're deep inside this boundary layer, and it turns out you don't really accumulate much of any charge on the surface of the particle. And as a result, the electric field lines, you can see them here, they're vertical, they're not at all being altered by charge that's accumulated on the surface of the particle. So as a result, this particle doesn't create this dipole, there's no instability, it doesn't move. It's only, if anything, attracted to the surface. So we can explain those two. If we try to do this dynamically, it turns out to be numerically a real pain, so we didn't try to do that. Instead, we're just going to come up with a heuristic description that describes the oscillations. So, the Goldilocks particles, they're just right. They're not too big, they're not too small. They're just the right size of this electric boundary layer. And as a result, they can acquire charge on the top side of the particles at rates that are faster than on the bottom side. At the bottom side, we're depleted of ions. They haven't yet fully ionized, right? And so the rates at which you can acquire charge on the bottom side are reduced. And so that suggests, a kind of hack solution to the leaky dielectric model, which is just to say, assume that there's a gradient in conductivity. Zero conductivity at the surface, bigger conductivity at top, and when you plug that in and you run the simulation, you get these beautiful oscillations that look very much like those that we see in the experiment. Here we're moving with the particle, so you'll see it moving. And sure enough, if you plot the angular velocity of the particle, you get these regimes, nothing, then rolling, then a second transition to oscillatory behavior. So we think this is a nice description explaining how you can oscillate in the absence of these inertial effects for these Quincke systems. So that was an exciting scientific mystery for us to pursue, but we're also engineers, and so we have to ask that question, who cares, right? Why do I care that this particle is oscillating back and forth? And the reason why I'm excited about this is what types of new model systems for active matter this enables. And this is inspired by work from Steve Strogatz on what he calls swarmillators. And the idea of a swarmillator can be illustrated by this example of a frog, right? So the frog is going to be croaking rhythmically. So these frogs go croak, croak, croak. And they croak all at the same frequency, but they have different phases, right? The two frogs might be croaking in unison, croak, croak, or they may be croaking out of unison, croak, 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 right? Depending on their respective phases. And then they're located at different positions. So you can imagine interesting scenarios where the phase influence how the frogs in this case, move. And the position of the frogs determines how their phases interact and whether their phases want to become more in phase or more out of phase. And so in a simple model, Strogatz and coworkers found these really interesting dynamic swarming states where the frogs could never just be happy, right? They were constantly looking around, trying to find a stable solution. And here this happens when like attracts like, so meaning frogs that are croaking in unison move towards one another, but in which the phase coupling is such that coupling increases the phase difference. So the closer they get, the more coupled their phases become, but they're repulsive, right? So their phases, they get too close, their phases become out of phase, and that leads them to repel. And so as a result, they're kind of chasing each other around in circles. Okay, so this is something that we see, not exactly, but we see these similar types of ideas in large collections of these particle oscillators. So this is just a taste of some of the behaviors that you see in this system. We're going to be increasing the field strength in this movie. And you start out in the rolling state, and they're kind of swarming, but then they start oscillating. And in this oscillating state, you can see these regions that form really dense, synchronized, oriented oscillations that kind of repeatedly blow up. So there's really rich behavior that derives from the fact that these particles have internal degrees of freedom. They're not just particles, they're particle oscillators that have phase, that have orientation, as well as position. I'll play one more time. So for another time, I will explain to you what they're doing here. Right now, we don't yet know, but we're extracting all this information about their oscillation phase and orientation and frequency to see if we can make sense of it through the lens of one of these swarmillator type models of Strogatz and company. Got to move faster. Okay, so part two, more quickly, this magnetic topotaxis. We're shifting gears to working on a design problem. This one is led by Young. You saw him in the previous work. And also by a really talented undergraduate named Peter Xelios. And first, let me take the time to set up the problem, and then we'll give you the results really quick. So it's hard to control the motion of these active colloids when you have only global actuation and limited information. So let me give you an example of what I mean by that. So here we're going to be using magnetically driven propulsion. So forget about the Quincke rollers. This is a magnetic roller. It rolls because you're applying a constant torque to it by rotating a magnetic field. So you rotate a magnetic field, the particle has a magnetic moment, it wants to rotate with the field, and therefore it turns and is coupled to the surface hydrodynamically, and it translates. And there was this really nice paper by Michelle Driscoll and Paul Chaikin, and Michelle showed us how to make these coils. And this picture shows nicely this idea that a common field drives common motion. All these particles experience the same exact field, and so here they're being driven to draw these rectangles. And this is really hard if you want to control them, for example, to solve this maze or to navigate through some structured environment to get to a targeted location, right? You can't make all of them do what you want them to do, right? Because you can only apply the same control action to all of them. But that's only half the problem. You can't see where they are, right? So you get this one global actuation of the field. You don't know where the particles are, and you want them to solve this maze, right? That's the challenge that we want to address. And so the question here is that can we use time-varying fields to direct particles to move in response to variations in their environments, right? So if they're going to solve this maze, they're going to have to make use of local information available in the maze, right? And the field is just going to provide the energy they need to guide that motion. So we've demonstrated this only in this really simple example that we call topotaxis, which is just directed migration on a topographic gradient, meaning you have a particle and it's on a plane surface and you just apply a slope to that surface, and the goal here is to migrate up the surface. The only reason we chose up is because it's counterintuitive, right? You know how to make it go down under gravity, so we want to make it go against the gravity direction. And if we can succeed in doing that, and I guess I should make one more point, which is that we don't know which way is up, right? So we want one field, no matter how you tilt the surface, the particle is going to go up, okay, in the same field. And we think of this as a design problem where we have a design space. We get to apply spatially uniform but time-varying fields. And we can expand that field as a Fourier series, so we can truncate this a certain number of nodes and say, okay, that's the design space. Pick the coefficients of the Fourier expansion, that's what you can control. All right, this is what it's going to do if it worked. Turn on the field, the particles go up the hill, right? This is cool because they're feeling the same magnetic field, but they're doing different things. Okay, and we're going to start by just doing this with a model, right? So no experiments now. We know how to describe very well a sphere on a solid surface in a viscous liquid at 0 Reynolds number. We know there is a magnetic torque acting on that magnetic moment. There's no magnetic force in a uniform field, and we know how the forces and torques lead to translational and rotational motion at low Reynolds number. And for this simple geometry, we know also these resistance coefficients. And then we need to know, just rigid body kinematics of how this particle is going to be rotating. This highlights a general problem that I think is going to face all types of challenges when we look to program colloidal robots, which is typically we have some space of design spaces. We can change different materials, different shapes, different driving fields, and we have some goal, what do we want it to do, and we don't know which design is going to lead to the performance that we want. And so we can use models, we can use experiments to go forward, but we'd really like to be able to go backwards somehow to a desired performance, back to the design. So being able to do this faster is something that we need to, as a field, to get better at. So here we're going to make use of some models and some kind of human insight. So it's not yet an automated process, but ultimately the hope is to accelerate this further. So one trick that we use, and this is always smart when you have a design problem, is get rid of unnecessary design space, right? You have a big design space, some of it is just not going to serve your purpose, right? If you can identify it, get rid of it, and design it with using fewer variables. So here we're going to use a symmetry constraint to say that the fields that we use have this symmetry where if you rotate yourself about the z-axis, the field looks the same. Okay, so here this has some n-fold rotational symmetry about the z-axis. And the reason why we do that is that if you put particles on a flat surface, those particles just wiggle. They don't go one way or the other because the field is not telling them which way to go. And so now we can reduce the dimensionality of the design space to 9 dimensions. So, okay. Okay, and I'll leave some time for questions and discussion. So I'm going to move kind of fast through this, but if you look at this problem through the lens of perturbation theory and the limit of small slopes and small frequencies, you can just expect, what is the migration velocity going to be? There's no dependence. It has to be dependent on the frequency. There's no frequency, there's no field, it doesn't move, right? So there's a first order effect in frequency, and within that first order contribution, there's a contribution that doesn't depend on the slope, it's just in the field, and then a contribution that's proportional to the slope. And then likewise, it's second order in the frequency. So what we get with that rotational constraint is we get rid of the things that we don't want. We didn't want this motion. We only want motion proportional to the slope. But unfortunately, we find that on a slope like this, at first order in the frequency, you're going to move perpendicular to the slope. You're not going to go up the slope. So we have undesired motions. We don't want those. And we have a desired motion, which is up the hill. So the goal now is we've kind of narrowed in the target a little bit better. Are there fields that will eliminate these undesired motions and maximize the desired motion going up the hill. It turns out there are such fields. Here's one that we just kind of found that works. It's not the best, but it just works and it's analytically tractable and it's useful to kind of demonstrate the idea. So this is what that field looks like. So I should interpret this like, you can think of the field as a vector, right? And the tip of that vector here is moving on the surface of a sphere, and it traces out that complicated curve. That's the field we want to apply. And it turns out if you do that, then you're going to get a migration velocity. It's going to go uphill. And that's what you expect the particle to do. Wiggle, 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 but slowly kind of make its way up the hill. And so I didn't say it would be efficient, but remember, the field is not doing the work just to pushing it up the field. It's telling it how to respond up the hill. One other point that's important to mention is this parameter. The reason why this works at all is because there's a difference in the resistance to rotation of a sphere about an axis that is perpendicular to the interface versus an axis that is parallel to the interface. If there's not that difference, this doesn't work at all. So beyond that, I have no intuition for why this field works. Right? It's a bit of a black box. So that's one thing we're working on. How can we make this more intuitive so we can actually guide design? And so Peter, the undergrad I mentioned, he did experiments in response to some unreasonable review requests, I think, to actually do this and demonstrate that it works. But being the motivated undergraduate that he is, and was, he's no longer undergraduate, but he still is that he was able to get this to work, that he was using larger spheres for which gravity was too much to overcome. And so we did this on simulated incline. So this is kind of cheating. Flat surface, tilt the field that we're going to apply, and show that that tilted field drives particle migration, not against gravity, but uphill as if it were going uphill. And sure enough, he finds that the particle on the inclined surface moves, whereas the particle on the uninclined surface doesn't move. And moreover, the speed of that migration goes quadratically with the applied frequency as predicted by that model. So the first step, and what I think is going to be an exciting system, which we can extend in lots of different directions. One is using particles in different shapes, because that increases the coupling of the rotational motion to the translational motion. So Jen, I think this is another picture of yours, perhaps. Some nice ellipsoidal particles. So this is with Bhuvnesh Bharti at LSU. It's providing us these ellipsoids to try. I mentioned automated experiments, right? We don't have a good model for ellipse. So how do we design a field that can drive a particle to move? We need a way to navigate that problem experimentally, but in an efficient way. And so we've been developing techniques to using Bayesian inference and experimental design to learn models and then use them to guide design processes. And then where we're really excited to go with this is topotaxis is one thing, but arguably a more interesting target is rheotaxis and the ability to move through fluidic networks like the vasculature in a way that requires no knowledge of where the particle is, but only using this field to tell it how it should navigate a system against the flow, for instance, or against, to swim away from the wall or toward the wall, guided by these heterogeneities in the environment. Okay, so I want to thank you all for your attention, and let me just acknowledge all the students that contributed to this work, but particularly to Jinyan for the Quincke oscillators and to Yong for the topotaxis. And this work was supported by a really unique center that has been very supportive of us. It's called the Center for Bio-Inspired Energy Science, run by Sam Stoop at Northwestern. It's funded by the Department of Energy. That kind of allows for us to explore these interesting bio-inspired directions to create systems that I think ultimately will have some real value and applications, but we're not there yet, but soon to be. And please ask questions or offer criticisms, especially to the students in the audience. I'd love to hear your thoughts. Thank you very much.
Thank you, Kyle. That great talk. Questions? Yeah, great question. So it turns out
So yes, we looked at shape, and it seems that as long as the particle size is commensurate with the boundary layer thickness, you'll get that oscillation. There are shape effects though, so I think the one shape that Shane looked at most closely was cylinders, and if you have a longer cylinder, aspect ratio greater than 1, they roll back and forth, right, like that. If you have a short cylinder like a disc, then it flips back and forth like that. So shape does not seem to determine, it's not a strong predictor of whether it will oscillate or not, but it may help to modulate the oscillation. And yeah, there are probably really interesting ways in which, now that you mentioned it, you could kind of rectify oscillations to drive other types of motions by using the effects of shape. So yeah, great suggestion.
So have you considered like interparticle is there any interparticle interaction?
Yes. So we were kind of pursuing, the many-body system. We were kind of pursuing this in parallel. One is just experimental. Let's just work out the phenomenology and see what the target is even to explain. Interactions, people have studied interactions between Quincke rollers and an unbounded system. And so here, we have the dynamics for a single particle from those simulations. So we can work out the electrostatic interactions, the hydrodynamic interactions, and how that leads to, and what are the interactions between the phase and the orientation. We have not done that. We'd be very interested if anyone is interested in looking into that. But that would be the kind of ingredients to a model that we ultimately would envision, which is to say, how do Quincke oscillators want to synchronize, or do they want to become asynchronous? Do they want to oscillate in line with each other or perpendicular to each other? We would love to have at least qualitative information from that model to say, we think they want to do this, right? And if you plug that in, do you observe some of the same qualitative features of the experimental system? Yeah, so that's kind of what we're thinking.
Questions?
Yeah, that's a good question. So this is no. That's the short answer. No. And this comes back to the fact this is not an uncommon surfactant for making these inverse micelles, and so it has the certain convenience as being a reasonably well studied system. There doesn't seem to be. I'm trying to think of a potential role that the for us, from my view, the surfactant is just a means of creating this generic charge carrier of a certain size, right? And it has to be a certain size. Otherwise, if it's too small, the electrostatic energy of making a charge in hexadecane is so great that you don't get the charge carriers, right? So once you have one that works, it checks that box. So yeah, I don't know. There could be interesting behaviors that arise. I'm thinking that if you have other morphologies at higher concentrations where you're no longer forming spherical micelles, if you're getting worm-like micelles, I imagine there's all kinds of exotic things that would start to happen that could be interesting to explore, but we've not thought of that. Yeah, that's interesting.
I have a question on your topotaxis. So when you go from topotaxis to rheotaxis, as you were discussing at the end, what are sort of the design parameters that go into that? Is it translatable fully from what you're doing with magnetics? And would this go up if you had a viscosity gradient? Would that go up that viscosity gradient? Or?
So the way that we frame this problem, which is that is basically to say, can I tell left from right? So like first of all, is there such a thing as uphill, downhill? And then do I have a design space that is rich enough that perhaps somewhere in there there's a field that can guide motion? And when we started, it wasn't necessarily obvious that would work, right? Because, like I said, I don't have intuition for why it necessarily works. It's kind of one order beyond what I have intuition for. So the same we've applied the same principles to the radiotaxis system for the sphere to say, okay, there's a flow that's creating a torque on the sphere, and you're basically leveraging that torque to then use a field that kind of takes that torque and then propels it upstream. It seems like it's harder in the sense that we can completely, so far the prediction is we found fields that completely arrest its motion. So basically, you turn off the field, the particle is washed downstream, you turn on the field, and it stops, according to the model, right? It can't quite combat the stream to flow upstream. So that's where things like the ellipsoids become important because they give us that kind of potential for stronger coupling that might have a better strategy for moving against the direction of flow. But my sense is that there's no reason why it shouldn't be possible in general for some shape. But that's kind of a conjecture that we're just working one system at a time. And why there's a need to accelerate that kind of discovery process of, I didn't mention it here, but another approach we use is just to, if you have a good forward model and can run it fast enough, just do brute force exploration of the design space, find the ones that are predicted to work, and then scrutinize them to have some sense of why is it working, and maybe you can learn.
What is landscape adding? That's agnostic. So do you think like, I've never seen this before, like kind of like the next look at micrometer.
Right.
Also present in other systems beyond where it is in electric field, you know.
The key thing is there's a term there which is the recombination rate. So you need that. I don't think you could get this in a strong electrolyte. So that's, I think, the key. And you know, we haven't. I'm often mystified by the facts that you're using the same descriptions to describe, you know, induced charge electrophoresis, contact charge electrophoresis, Quincke, you know, and it's all because you're in slightly different regimes of the parameter space where experimentally they just feel very different, but even if they're all in one framework. But I think here the key thing is that ionization recombination. I don't know of an analog. We encountered that same phenomena. I don't know if Jerome is still here, but the flames in Whiteside's labs, right? So flames create plasmas, and they have exactly these mechanisms of ionization and recombination. And that turned out to be important when manipulating flames with AC electric fields. So I'm happy to say that flames work was not completely useless, right? We were able to learn, you know, it was relevant here. But I don't know if it applies to most electrolytes.
Perfect. I think we're actually right out of time, so let's thank Dr. Bishop.